Can the online students hear me, and can you see my slides? All right, all good. Slides are on the lectures website. All right. All right, let's start with a revision of what we did yesterday. So concurrent processes are processes whose execution overlaps in time. So if a process A starts before process B and continues executing after process B, if their execution overlaps in time, we say that they are concurrent processes, even though they may not be running at the exact same time because there is only one processor or one CPU. So a process is either executing instructions or it's waiting to be executed. The operating system may at some point decide to context switch or schedule out a process and schedule in a different process based on some policy. We talked about private address space. Each process has a private address space. This address space is virtual for the moment. We will look at virtual memory tomorrow. If it's a 32-bit process, 32-bit architecture, then the process has the entire 4 GB address space to itself. Now, this is not possible, of course, if there are multiple processes running and we only have 4 GB of physical memory. We cannot have 8 or 16 GB memory for each process. So we create an illusion that each process has the entire 4 GB address space to itself, just like we create an illusion with the process abstraction that each process has their CPU to itself, even though under the hood, the operating system is doing things to make it look like that, but it's only one process running at a single time, executing instructions. So we have the same abstraction for memory, which we'll look at next week. For now, you just need to remember that each process has a virtual private address space. And you can think of it as consisting of the kernel area, stack, heap, global segment, read-only segment. It's a picture you might have seen in lab 3 already, where we show you that there is a dynamic data segment, there is a stack, there's a heap. So each process has the illusion that it has all of these segments, all of these areas in its private 4 GB address space. Under the hood, multiple processes have to share 4 GB physical memory, and somehow the operating system creates the illusion. Right, so that's the concept of virtual memory, and the operating system uses storage or disk as an extended main memory or memory. And we will see how it does that. It does swapping, it does a lot of other things to make it look like as if each process has 4 GB. Under the hood, it's using storage devices, disks, solid state drives as an extended main memory.
Could very well could be wrong here, but does your system start to use the physical storage once the RAM runs out?
Right, it does. And we will spend a lot of time next week, in fact, the next 3 weeks probably on that. How the operating system does that, how it uses storage devices, disks, as a form of extended physical memory. Because it doesn't have, if there are 100 processes, we don't have 40 or 400 GB physical memory. We only have a physical address space of 4 GB, and the OS somehow manages that. All right. So the picture I want you to remember right now is each process has the illusion that it has this address space from 0 at the bottom, at the top 4 GB. The operating system's kernel reserves a portion of the memory at the top. This is where the kernel code and data resides. And so every time there's a system call, every time the kernel has to execute some code, this is the area where the kernel's code and data is present. The kernel is obviously stealing the address, the space, or some portion of the address space from the process. It's partitioned into different segments. You already know about the stack. And if you have done lab 3, you already know about the heap. There's a bunch of other things here which we will cover over time. Read-only segment, global segment, all of these things. The process thinks that this sort of an illusion, this 4 GB of virtual illusion address space is actually a physical address space. That's not true. And somehow multiple processes share physical memory, which we'll look at next week. We talked about user and kernel modes. I'm just revising quickly what we did yesterday. So processors have a mode bit in a control register that specifies the privileges the process currently have. We want to prevent the user processes from executing certain type of instructions that could be very dangerous, harmful, accessing an IO device, halting the processor, changing the mode bit. If we give user programs, the applications you have been writing so far, the privilege to execute such instructions, then the process abstraction is not very airtight. One process can do something that will hurt all other processes. So we only want to let these things happen in kernel mode. So the kernel has the responsibility to execute such instructions. So every time, so when this mode bit is set, the process is running in kernel mode. And when this mode bit is not set, the process is running in user mode. And so process running in kernel mode can execute these privileged instructions, and these are the examples, as I was saying. So user programs can only access the kernel code and services via the syscall interface, which is a synchronous exception or a trap. We looked at it yesterday. So whenever there is a syscall, the processor actually goes to a trap handler. And the first thing it does, it changes the mode bit. And now the kernel, the trap handler can execute an instruction in the ISA. So this is one way to go from user mode to kernel mode. The other way is, of course, there is an interrupt, there is an asynchronous exception, something happens in the environment. So if you look at this address space here, your code that the application is running, if there is no system call in your code, a bunch of for loops, if loops, that kind of logic, you are somewhere here. And the code is somewhere here, somewhere here. The text, historically, we place the code in the text segment. All right, when there's a switch to kernel mode, you're running the code somewhere in this little area. So this is a very clean interface, this division between user mode and kernel mode. So syscall exception is a general term. Syscall is a type of exception. It's a synchronous exception. The handlers then run in kernel mode, and this is how the user to kernel mode switch takes place. Kernel, once again, is a very small component of an operating system that, as we will see in the future lectures, is always resident in memory. It is not present anywhere else. The other parts of the operating system may be on storage device on a disk, but the kernel is always in memory. It's a critical component that we need very fast access to. Context switch is used to implement multitasking or time slicing. The basic idea is each process executes for a while before it is, the word here is preemption. Preempted, it means temporary suspension. So the kernel, at some point in time, decides, hey, this process has ran long enough to be fair to other processes. Let's preempt this process and bring another process in. So the kernel saves the context. Context consists of the register file contents, flag register, these kind of things. So the kernel saves the context somewhere in memory and brings another process. So the kernel saves the context of a process. When the process is suspended, this is called scheduling a process out, and restores the context when the process is again restarted. And this is called scheduling in. Scheduling out, scheduling in. Save the context, restore the context, bring the context of a different process in, and all of this happens through interrupts, exceptions. The portion of the kernel that does all this is called the scheduler. We won't be going into the scheduler. This is the domain of operating systems. We just want to know that these things exist. And typically, there is a scheduling quantum or period that the kernel uses to decide how often to switch, to schedule in and schedule out different processes. So context switches happen on certain events. There are blocking system calls. Imagine the program doing a read system call, reading a file contents from disk. Disks are so slow compared to the processor and memory that if it takes one day to get something from memory, it takes a few years. I'm using an analogy. It takes a few years to get something from disk. Disks are really, really slow. A few milliseconds versus a few nanoseconds. That's a huge difference in latency. So the kernel decides, hey, this process is going to wait a really long time. It's a system call. Let me bring a different process in. So this is how context switches takes place. Different policies, different operating systems, different kernels use different policies. This is one way to think about it. Every time you have something the process wants to do, the process wants to use a service from the kernel, and that service will take a long time to resolve. The kernel decides, hey, let me do a context switch. Let me save the context of this process, bring the context of a different process. So sleep system call processes can go to sleep. There are many reasons for that. Not every process runs forever. They want to perhaps wait for an event to take place or an interrupt. And then there's a timer in every computer. And this timer helps the kernel to track time. And every 1 millisecond, every 10 milliseconds, the kernel has a way to measure time using this timer interrupt. Have you looked at timers before 2300? So this timer interrupt is generated by a separate chip that is, it may be outside the processor or inside the processor, but it tells the kernel that it helps the kernel to track time. And every 1 millisecond is 1,000 of a second. That's a long time in the life of a processor, which is running at 2 gigahertz, 4 gigahertz. Or every 10 milliseconds, there's an interrupt that is generated by the timer circuit, and then the kernel and the CPU together treat it as an exception and do a context switch. Okay, so this is how processes share a single CPU using exceptional control flow. So doing different things at a time, and giving software the illusion that each process, each program, each running program, a process is a program in execution, has the entire CPU to itself. This is a copy. This is from the previous lecture slide. So here, imagine that process A is running, and then there is some kind of an interrupt, some event, maybe a system call, maybe an outside event. Here is the context switch in pink. The kernel takes control of the CPU, and here it's probably doing a bunch of things, such as saving the context of process A. So now it's doing a context switch, but first of all, it's running on behalf of process A. And then it restores the context of process B. So save here, restore here. And then it starts running the process B in user mode or user code, all right? So this is how context switches look like pictorially. Vertical axis is time, and then we are showing two processes. We were looking at fork. So every time there's a fork, this is a variable PID. Now, whenever we call fork here, there are two processes now in the system, the parent process and the child process. PID is fork is kind of special. It is called once and it returns twice. What it returns to the parent is the process ID of the child, which is always greater than 0. And what it returns to the child is 0. So there is no ambiguity in figuring out who is executing the code from this moment forward. You can check if PID, at this point, there is only one address space. Beyond this point, after fork, there are two address spaces. So the address space of the parent, the kernel takes a carbon copy of that. It is copied one-to-one and gives it to the child. But any changes after fork are private to the parent and the child. So PID here, at this point, PID is not even initialized in this code. after this point, the parent will have something greater than 0, which is the process ID of the child. This is the parent, and the child will have a process ID of 0. So with the if statement, we can check which of the two processes, parent or child, we want to are executing this if statement. Yeah.
When a fork is code, is like everything in the stack and in the like program memory, like copied and duplicated?
Right. So everything, user stack, data segment, dynamic data segment, everything is copied for the child process. But after that, after fork, the if statement and the return value of fork, all those changes are private to the parent and the child. Now, after fork, the kernel can decide to run, if we have only one CPU, the kernel can decide to run the child or the parent. It will have a policy for context switching. So we can never be sure which of these print statements will appear on the screen first. And that's the non-determinism in concurrency. The parent and the child at this point are concurrent. After this fork, they're running concurrently. And this is where a lot of problems appear that are relevant to concurrency. So here, if you do it in your lab machine or your laptop, you may get the child first and the parent second. And each time you do it, you can never predict. And that's the world of concurrency. So you remember that fork is called once and returns twice. At this point, we are looking at concurrent execution. And you cannot predict the execution order. Duplicate but separate address spaces. So X has a value of 1 when fork returns in parent and child, but subsequent changes to X are independent. So here, plus X, X child has a copy of X, parent has a copy of X, and so this is how web servers, shell, other programs on the World Wide Web, they make heavy use of fork, and we will keep exploring this over time. And any files that belong to the parent, the child gets share the files. So here, the reason child can print on the screen is because every process has 3 files that are created for it by default, std error. Every running program has 3 file descriptors or 3 files that are created for it by default. And these 3 files are also shared by the child, so it can use the standard out file to write to the screen. Okay, the file abstraction, we will spend a lot of time, but for the moment, everything, file is a very powerful abstraction in Unix-like operating systems, and standard input, a stream of bytes that you input from the keyboard and any other device, standard output, standard error, these are all treated as files. And each file has a file descriptor. You already probably have used standard in, standard out in your labs. And so these files are shared by the child.
So what the parent and the child process request something back info to activity out. So we did there any like those conditions?
Exactly, that's what I'm talking about. One of them will go ahead and print first. The other one will come second. Right. So if you run it on your machine, you might get child first. We looked at this one. I think this was spent some time there. So the parent executes all these statements, L0. It does fork here. Then it does a second fork here. and then it goes to buy. So this is the parent. The last fork that it does, that child, the child that is created at this point, only executes the buy. And this child here does a printf, another fork, and a buy and a buy. So you end up with 4 processes. This is just for, we don't necessarily need to write confusing code like this. This is just for illustration. Okay, so any questions about from online students as well? Processes, is fork clear? Is there any confusion at this point? So we were talking about reaping child processes. When a process terminates for any reason, the kernel does not completely remove the child from the system. You can think of reaping as you reap what you sow. This is an old saying. So if the parent plants a child, it has a responsibility to check upon, what was the outcome? Did the plant survive? Did it die? What happened? So a parent has to reap what it sowed. Okay. The child can terminate at any point. The parent can continue executing, but it is a good practice for the parent to reap a child. The child is kept around until the parent reaps it. And a terminated process that hasn't been reaped yet is called a zombie. It's terminated, it has done its work, but it's still around, consuming some resources. Now, reaping is performed by 2 system calls, wait and wait pid. Now, at this point, we are looking at system calls. From next lab, you will be writing system programs where you will use system level functions or system calls. So all these are now system calls. The parent is given the exit status information when it reads a child, and then the kernel finally deletes it. If a parent does not reap a child and terminates itself, or it is terminated, then the zombie process is reaped by a special process called the init process. And the init process has a PID of 1. So if the parent process runs for like a minute or 5 minutes, it doesn't really need to reap all the child processes, because the init process will reap those child processes anyway. But imagine a Gmail application running in a data center or something that runs for months and months. And if that application, if that process creates a lot of child processes and doesn't reap them, it will eventually consume a lot of resources, memory resources, other resources. So long-running programs, applications in data centers, mail, they really need to be careful about reaping the child processes and not letting these zombies in the system for too long, right? But if a process runs for like 1 minute, 5 minutes, does something quickly, the init process will take care of the zombies itself. Here's an example so we are forking here. So fork equal 0 at this point means that this if statement will only be executed by the child, because the child gets a return value of 0. So the child executes a printf statement and then exits. So this is an exit. This exit is used for a process to terminate itself, to exit. The other way to terminate, for a process to terminate itself, is to call return 0, execute return 0 in the main program. And the child process and the parent process here runs in a while loop. All right. So do we have a zombie in this example? Right? The parent is running, but the parent hasn't done anything special to reap the child, which has exited. And if you don't see a wait or a wait PID in the code, it means that the parent has not reaped the child. So here, if you type PS, so here in the next lab, you will run this program forks there are different examples that you will look at the output. And so PS is a command in Linux that prints out all the active processes, all the processes. So if we run this program, the parent has a PID of 6639 and the child has a PID of 6640. And if you look at all the processes, you'll see that the child is defunct and the parent is still running. The parent is running in a while one loop, right? It's never going to terminate itself. When we kill the parent here we are killing the parent. 6639 is the PID of the parent. When we kill the parent and we again check the list of all processes, we don't see the child process because the init process has reaped the zombie, right? So you can do this. Next week on the lab machines or on your computer, and you can verify yourself which processes were not reaped by the parent, but were reaped by the init process. Okay, so what's happening here is the child is running in an infinite loop, and the parent exits without reaping the child. So what will happen here? Is there a zombie here? Right? There is no zombie because the child has not terminated, right? The child is running forever, but the parent has terminated. So what happens here? What will the init process do here? Intuitively, will it reap the child? Not really, because the child has not terminated. Whoever wrote this program, it's a buggy program. It's a bug. This while loop in the child will run forever. The child will never terminate. There is no zombie, right? Unless there is an exit here somewhere before the while one loop, this child will never terminate. It will just keep consuming the CPU resources, right? The only way for a zombie, we will have a zombie if the child terminates and the parent is running, or the parent also terminates without reaping the child. So here we will have to explicitly kill the child process with a command. So this is a shell. I'm not showing you the shell. Shell is a program that lets you type different commands, and then it read those commands and evaluate those commands for you, and then read the next command. I think you've been using the shell. You're all using the shell in the labs for when you do make and other things, right? Okay. When you open a terminal, it gives you a shell, and then you type all your commands. That's what we call the shell. What? Terminal is an application that gives you an interface to the shell. But you can think of them as the same. It's an application that that lets you run other programs on your behalf. So you can open a shell and start running different programs. instead of running them by double clicking on a desktop icon, you can open a shell and run different programs, different commands, right? And yeah, you can think of terminal and shell the same, but typically you can have many different types of shell, bash, but terminal is one way to access a shell. Yeah. No, because a child is never a zombie here. There's a while one loop, it's always running. So how do we use wait? All right. This is how wait looks like. The default behavior of wait is to suspend the current process until one of the children terminates in the wait set. So we will soon look at what is a wait set. And it returns a value. This value is the PID of the child process that terminated. If the child status, this thing here, is not null, then the integer it points to, this is a pointer to an integer, will be set to a value that indicates the reason for termination and informs us about something about why the process terminated, what happened. Now, interpreting this integer is really confusing. So the wait.h header file provides different macros to see what happened. All right, this is an easy way to see what happened to the child process. So here's an example. So we are forking a child, and the child printf and exits. Now clearly there's a zombie in this example, right? The child process is terminating itself. Okay, so this is a zombie. The parent does a printf and then it reaps the child. Okay, this is called reaping the child. So, and at this point, after this wait, the kernel will remove any trace of the child process from the system. The zombie will be dead instantly. All right, unlike the movies where it takes about 2 hours or so. All right, so here is how we can see these. If we look at the process graph, the parent forks, does a printf, and then calls wait, and the child, after exiting, the child and the parent meet at this point, and so this is called, the parent being responsible is reaping what it planted, right? So, and so we are passing this integer here. So we create an integer variable, and then we pass the address of this variable to the wait call, and the wait system call or wait system level function will set this pointer to an integer variable, right? So this this will tell us something about the child process, why it terminated. Right, so it takes a pointer, and then internally, what will it do internally to set a value? for the child status very quickly. So if I pass the pointer to this variable like this, internally weight will do what? To set the value to something, 1, 2, or 3. What will be here? Star? Okay. So I'll give the point, I create an integer variable and I give the pointer to that variable to the weight system call, and then it will use the address of the variable to set the value to something that will inform me, that will tell me something about why it terminated. And I can use these macros to investigate what happened. And the definitions of these will give you these in the next lab. They have intuitive meanings, W if exited, W exit status, blah, 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 and then we'll give you we'll give you a sheet to tell you what you can do with these. All right, here's another example. Okay. So here we are using these to get information about the process. Okay, so we are creating n processes, n child processes, and we are storing their PIDs, their process IDs in this array. Okay, so the parent gets all the process IDs in this array of process IDs, and the children all just terminate with an exit status that is not ambiguous, something 100 plus I. Okay, so I just want to point out that, so then what is the parent doing? The parent is reaping all the children one by one. So I equals 0, I is less than n. Each call to wait returns after one child process has terminated. All right, so for each child you want to reap, you want to call wait exactly once. One call to wait will not reap all the children. So here we have a for loop, I is less than n, and we reap all the children. The question is, in which order are we reaping the children? Are we reaping the children in the same order in which they were created? Not really. Wait, this semantics, the meaning of the wait system call is, I want to stretch my legs a little bit. Whenever one of the children in the weight set here is all the children that process has created. When one of them terminates, return the PID of that terminated process, right? And it's by default, it suspends the execution of the parent process. So when wait is called, the parent process is suspended. It is not doing anything. It's just waiting for one of the children to be terminated. And the kernel tells the parent, here is one child that terminated. And then next time the parent calls wait, the kernel tells, here's another child that terminated. But they are created in this order here. We know the process IDs in this array, but they are terminated in no specific order. What can we do to reap the children in the same order that we created them? What can the parent do to reap the children in the same order that it created? So for that, we have the wait PID system call. Wait PID system call is different. It takes a specific PID that you want to reap. It takes a specific PID that the parent wants to reap. So since we have stored all the process IDs, since we have stored all the process IDs in this array, the parent can then use wait PID and pass the actual PID of the child it wants to reap. Now, are the children now reap in the same order in which they are created? Right? Yes. So I equals 0, I is less than n, I equals n minus 1, 0. If I use, instead of specifying a specific PID, if I say -1, then it has the same semantics as the wait system call. Then it returns when any child in the wait set terminates. And there are different options here. Sometimes the parent doesn't really want to suspend its execution and want to continue. If no child has terminated, the parent be like, oh, okay, whatever, I'm going to go continue doing something. So those options will be in the lab next week. And you will play with all this, and hopefully it will become more clear at that point. Okay, so far, what we have done is we are running programs where a process runs the same program in the context of a different process by forking a child, all right? So initially, there is only one context, the parent process. And then after fork, there is the context of the parent and the context of the child, but they're actually running the same program. We are now going to look at how can the parent process run a different program, right? So you might have a program, hello, inside, when hello is executing, it may want to run a different program called, my world, something like that. So we are now going to see how we can run programs, different programs from the context of the parent process or a specific process. And this is really powerful this is how shells are implemented. This is how web servers work when they take requests on behalf of users and run different programs that the users want. When you run something in the cloud and stuff like that. So the system call we are going to look at, there's a question here. How do we actually get the child status? The variable is never given a value. Yes, but the value is set by the wait system call. We give the address of, okay. So the exec is a family of system calls. The one we are going to look at is exec VE, loading and running programs using. So the first argument is the program that we need to run. This could actually be a command or a script. We look at examples in a little bit. And we pass the arguments to this using this. And then there are environment variables that are passed using the last argument of the exec VE. So the interesting thing about the exec family of system calls, or exec, is it runs a new program in the context of the current process. So it does not create a new copy of the address space. It does not actually create a new process. It overwrites the code, data stack, the address space of the process that calls it. So fork is weird, but exec is, more weird. So fork is called once and returned how many times? Twice. Exec or exec VE is called once and never returns unless there is an error. It starts running the program that is specified by the first argument. And it overrides the code, the address space of the process that calls it. So here is the structure of the stack when the new program starts using the exec system call. At the bottom, so if we go from top to bottom, here we have all the environment strings. Environment strings are when you want to set environment variables outside the program that tells something to the program. For instance, you could set the number of maximum files the program can open, the maximum size of the stack the program can have, and then the program can look at the environment read the environment variable, and you can set these environment variables using a shell command. Just like you type make, you can say set blah equals blah. And this is a way to make programs behave. So programs need to read these environment variables and then do something. So what we have here is environment variables, command line strings. So the programs, when you run a program, I don't know if you ran array 1, 2, all of these are stored here. So these are the command line strings we're talking about. These are just pointers to the actual strings. So you might notice that this is a, what should we call this? Array of pointers or pointer to a pointer, right? So this is the number of arguments are stored in a register RDI. The address of the list of pointers is stored in RSI. RDX has the pointer to the array of pointers that point to the environment variables, and then, okay. So let's look at an example. So imagine that we set up these arrays outside the code here. So we create all these arrays of pointers and all that, and we set them to these values, bin ls, and these are the environment variables. Okay, you guys have seen, has anyone seen ls before? All right, so ls is a shell command that is used to list all the files in the current directory. So here we are trying to imagine you're writing a C program and you want to execute the ls command from within the program. All right, so now we are talking about, we are moving towards how do we write shell programs? How do we actually write these programs that we have been using? All right, so we set up all these arrays outside the program. I'm not showing the code here, but you will have the code next week in the lab. And then we execute this in the child process. So the first argument is always the program that you want to run. So that is ls here. And then the second argument is lt. The third argument is this. And then there is null. And once we set up all these arrays, we first do a fork. Because if the parent wants to run, imagine this is a parent, and it wants to run many different programs on behalf of the user, right? If the program calls exec ve without fork, what will happen? The parent's address space will be replaced by the program that it wants to run. And then what? That's it, one program. We don't want to run one program. If you look at the shell as a program, as an application, you open a shell, you have a command prompt like this. So you run ls, it lists all the files, and then it shows you the command prompt again, right? And then you type something else, make, and it shows you again. What is it doing? Read, evaluate. Okay? So it's doing a bunch of read, evaluate steps. Read the command, evaluate whatever the user asks it to do, and go back again. And keep doing it, keep doing it, keep doing it. It cannot do that if, as a parent, for each command it reads, it calls exec ve. Because the exec ve will hijack its address space and only run one command. It needs to run many commands. So for each of these, it does a fork. It creates a child. Then it does exec ve. Now, the exec ve here hijacks or overwrites the address space of who? The child, right? The parent is still running. The parent has its own address space. That is a shell program. The child will execute this program, this command here, bin ls, and exit. So exec returns something less than 0 if the command is not found. Otherwise, it never returns. Otherwise, it just executes the program that it's asked to execute, and that's it. Never returns. The only time it returns is if something wrong happens. And we can check for that by looking at the return value if it's less than 0. Okay, I understand this may still be a little bit confusing, but what's happening here is, I'm not showing the code here, but we set up all these arrays. We set up all these environment variables when we write a C program. We set up all these arguments, and then we pass it to the exec. Do we have to wait for an exec to a shell function? No, because exec never returns. It's a different, we are not forking a new child process here.
And except the that is a question there.
No.
And what's the point of this?
Wait, no. The if statement, if it returns something less than 0, we need to know that, right? We need to print that here. Otherwise, it will just run the program successfully, and that's it. If it cannot find the command, then it doesn't do anything. Then it doesn't override the address space and anything, right?
How is the behavior?
The problem we're doing, so you're saying this? But if we just run exec by itself, and the user types a program, for instance, the user types a binary. Let's say I say ls, instead of saying ls, I say lss. But there is no such thing as LSS. So how do we know that the user did something wrong? But we need to check if the error is less than 0. It returns if something is wrong. If everything goes well, it never returns. If something goes wrong, it returns a negative value.
If except the boys returns number that negative.
It only returns if something goes wrong.
So can it return something that isn't negative?
No.
And what's the point of having a stable if it will always return 3?
Right, so it's possible to do that, yeah. Okay, I see what you're saying. If it returns, then we will go to printf. Yes, you're right, it's possible to remove the if statement. Good. Let's check that in the next lab, what happens. Right, so we could do that. Code readability. Once you have statements next to each other, anyone reading the code may not be able to guess what's happening. It's a good practice to perhaps check for. Okay, so I want to point out that you don't really need to know. Yeah, like you don't really need to memorize this stack, pointer to a pointer. I know it could be complicated. You need to set up all the environment variables and everything in those arrays, these arrays, and then call exec v. The idea is that you're no longer running commands from the shell prompt. You're actually writing your own shell at this point, a very basic shell. So if we look at a Linux process hierarchy, so in it, we already talked about, it does a bunch of things. In some versions of the kernel, there's also a process with PID of 0. Okay, we won't really talk about all this, but if you type PS3, you can actually see the hierarchy, and you will see a bunch of login shells. So whenever you log into a machine, you're actually given a shell where you can type commands, right? If you don't have a graphical user interface and all that. And shell is just a program that does a bunch of read, evaluate steps. It passes your command, and then it does something, and then it looks for the next command. And you can access different types of shells using a terminal on a MacBook, in VS Code, all that. So C shell, TC shell, Z shell are those examples of the learning to seeing how the shell is implemented will help you think about how web servers, web applications, when we move to networking part, are implemented. Okay, so here is how the main program of a typical shell looks like, a very basic shell. What we are doing here is, so fgets, I will show you a lot of, I'll use a lot of functions here, which are all defined in a header file that we will give you. You won't have to read the code. You will just have to read the English of what that function is doing and just use it in your programs. So, but here, if we start talking about what's inside each function, the slides will, we'll have a lot of text. So here, basically, I'm reading from the command line whatever the user is typing from the keyboard. So ls, make, gcc, all those things I'm trying to read using the fgets function. And then I'm printing this very nice prompt to make it look like a very interesting shell program. And I'm doing it in a while one loop. I never terminate unless the user terminates a terminal by, Okay, so in a while one loop, I'm continuously reading and evaluating commands, okay? Now, how does the eval function looks like? So here's the eval function. Once again, we are setting up the arguments, all of these arrays here. So parseLine is a function that we will give you in the lab, but we won't give you here. I'm not showing it here. It does a bunch of text processing to make sure that the user typed the right command and it isn't garbage and all that. What's happening here is, so whenever you have a shell or a terminal, you can do two things. You can type a built-in command, or you can run a program. What are examples of built-in commands? Printf is a C library function. So ls cd grep. What's an example of what do I mean by running a program? Right. So imagine all the programs that you're writing in the lab, array, string copy, blah, 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 like tons of programs in each lab. And if you're in the same directory as your lab folder, lab 3, for instance, and something here, and you type /array, then the shell needs to shell now has a job to do. It needs to figure out if it's a built-in command. So /array is not a built-in command. So shell needs to run a program for you. You're asking shell to run a program. So here, the shell is making sure it's not a built-in command, because if it's a built-in command, the parent process can just run it. right? The shell knows how to do the built-in command. I don't have the function here, built-in command, but it would be just, looking at the command and doing something it knows how to do. But the shell doesn't know how to do array. For that, it needs to run your program, right? So what is it doing? It's actually forking a child and then calling execve to run the child by passing all the arguments and environment variables here. And then it exits. Once again, we have the if loop here. All right, so I want you to focus on this part. So this is the part that we already looked at and we understand. If it's not a built-in command, so built-in command would be a function. Built-in command would be a function that would check to see if it's a built-in command shell, built-in shell command like ls or cd. And that function will just execute the code corresponding to that command. But if it's not a built-in command, then the shell needs to run your program, and it will do it using the combination of fork and execve. Okay. Now, what is happening here? So this is the child, and it's done. What is the parent doing here in this part? Okay, so there is a variable background. Whenever you run a program in shell and you type ampersand, the program actually runs in the background, not the foreground. Okay. It means running in the background means you actually get the prompt and you can type something else while the program runs in the background. Foreground means that you cannot do anything with the shell until the program terminates. So if you just type /array, the shell is not available for reading new commands. But if you type /array with an ampersand, sorry, my ampersand is a little bit messed up. This is an ampersand. The program will run in the background, and the shell, you will have the command prompt available to type a new. So we have this variable here, which checks to see if the program is running in background or foreground. So here the program, the parent is waiting, is reaping the child. It forked in the foreground. So wait PID, PID here, and everything is else is the same as we looked before. But at this point, we don't know how to reap a child that is running in the background. So do we have the code for? Okay. So we will look at how we can reap children that are running in the background. But this code here shows that how you can reap, how the shell program is reaping children that are created in the foreground using a combination of fork and exec VE. So I want to continue with background with signals. Let me give you a quick introduction to signals, and then we'll continue with signals in the next lecture. So far, what we have looked at is we could have interrupts, exceptions, but at this point, we haven't looked at a way for the kernel to communicate that to the process. Signal is a small message that notifies the process that an event of some type has occurred in the system. Now, each signal corresponds to some type of event, and signals are a very primitive form of inter-process communication. Processes communicate with each other using signals, and the kernel also communicate with processes, with user processes, by sending signals to the processes. So imagine that there's a divide by zero exception, and the CPU goes to the exception handler by using a jump table and start executing the handler code. And the handler code is running in kernel mode. But at no point have we informed the user process that something has happened. The kernel, after running the exception handler, needs to tell the user process that something has happened. And the way we do that is using signals. And you can think of signals as a form of software interrupts that provide a mechanism for handling asynchronous events. Each signal type is associated with a small integer, and each signal type is corresponds to a specific event. Okay, so here are some interesting events. All events have an English name, a default action that the kernel takes when it sees an event. So whenever you type Control-C from the command from the keyboard, all the processes that are running in the foreground in a shell actually get a SIGINT signal. And the default action for the kernel is to terminate the process. So if you have a shell, if you fire up a shell using a terminal, and you type a nasty program that does nothing but a while one forever, and then you compile it and run it, you will not get the command prompt. You will not see the command prompt again, ever. Why? Because the program is running forever. The only way to get the command prompt is to send a signal to the kernel or send a signal to the process, hey, stop, terminate, right? And one way to do that is by typing Control-C from the keyboard. And on some systems, it's Control-Z. We will give you instructions moving forward. If you're on Windows machine, type this. If you're on that machine, type this. So what happens is the signal with ID2 SIGINT is sent to the process. The kernel interferes. The kernel either takes the default action, which is to terminate the process, or it runs a signal handler that the program or process installs. So the process or the program has a way to inform the kernel, hey, whenever I'm in the foreground and you see this specific signal, don't do what you do by default. I want you to run this code. And it's called a signal handler. And by now you should have an intuition, how would this signal handler look like? How can you install a signal handler? We use function pointers. So that's why we introduced function pointers in lab 1 or 2, I forgot. So if you haven't done that exercise with reduce, you should do it. Have you done, all of you done that exercise? Okay, so you know function pointers. So the program can write a function called signal handler, and it will just install, it will give the kernel the pointer to that function, right? And the kernel will know, hey, if I get this signal, I need to do this for this program. Kernel sends a signal to a destination process by updating some state in the context of the destination process. So the kernel can send a signal for two reasons. One is something wrong happens. Divide by 0, segmentation, violation. You have an address that goes to some place in the virtual address space that you are not supposed to access. For instance, by now you should have intuition. If you have a pointer and you do something wrong, you assign it a random value, and then you try to dereference that pointer, you might be accessing kernel code. Who knows what is in that pointer, right? But you are not allowed as a user program to access the kernel code. And that's why in the lab, many of you have been getting this segmentation fault. So historically, it's called segment violation or segmentation fault. You're trying to access a region in memory. The user mode bit is set, the kernel mode bit is not set. You have a nasty pointer that is set to some random value because of some bug in the program, and you're trying to dereference that, right? The kernel says, hey, don't do that. You know? So it sends you a sig SVE sig signal, and the default action for that is terminate, right? So every time now in the labs, you will have a lot of this segmentation violation, the beauty of C, okay? The other way for the kernel to send a signal to a process is using the kill system call. And that's what I was saying is a primitive form of inter-process communication. So processes can communicate with each other by using the kill system call. So if any of you have ever used the kill application from the shell, you can actually kill a running process. If you have the process ID, specific process ID, you can use a kill utility to kill the process. And internally, this utility uses the kill system call. So shell as a program is communicating a signal to a message to a different process. So here is how so processes can ignore the signal, terminate, cache the signal, and do something interesting. They do it through the signal handler, which pretty much looks like the exception handler. So this is how the flow control looks like. Anytime the signal arrives, the kernel runs the signal handler code. Actually, the signal handler code is user code, but the kernel intercepts the signal, and because it knows the signal handler code is where is the signal handler code, we have a way to tell the kernel where is that code. We will see in a little bit. It can run that code and then go back to executing the next instruction after the handler. So these signals are asynchronous events. We say that a signal is pending if it is sent but not yet received. Okay, so the program has specified a signal handler but it hasn't yet received the signal. The signal is pending somewhere. The kernel is smart to not always interrupt the application. So it does something special. At special points, it tells the program there is a signal waiting for you, okay? There can be at most one pending signal of any particular type. So if from the command line, if I keep typing Control-Z, 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 there are not 10 pending signals. There's only one pending signal. Signals are not queued. If a process has a pending signal of type K, then subsequent signals of type K are not sent to the process and are discarded. And a process can actually block the receipt of certain signals. And this is very important when looking at concurrent execution, concurrent processes, because signal handlers and the rest of the code can have shared global variables, other things. And the process may say, look, I want to block all the signals because I'm going to do something really, really critical. And I don't care about signal handlers at this point. I don't want to corrupt my linked list. I don't want to corrupt my array. So I'm going to block the signals. And then when I'm back, I'll take a look at the signals, okay? So we do have the API to block certain signals. And there are, I think we're over time. Let's continue next week. And signals and background jobs are very related. I'm going to bring back how background jobs work in that code that I showed you, and then connect it with the signals and how we can do that. I know that is a part where we kind of got stuck. All right, thank you.
I have not enrolled your course cs.courses but I still cannot access the foreign my computer.
Can you send me an email with the?
I send you an email about.
Then I will add you at some point.
So what?
I will add you today.
Okay.
It's like a software exception. It's similar to an exception, but it's a software exception. Are things making? Is it okay?